later, anytime you like. So in our notebook, right after lesson 5, there's like a graphing assignment in there. And that's what I want to work through with you guys today, because lesson 7 is basically the entire thing is word problems and graphing different things. So lesson 7 is a fake lesson. We're going to do some practice problems together, and then I'll tell you what to do next. So the assignment, graph 2 cycles of the following equation. Okay, things we need to notice. We are looking at a sine equation. We are looking for key features. There's a 3 plus pi by 6, a 2, and a minus 6 there. These pieces of information tell us certain things about our graph. The amplitude is 3. So that means we are going to be, this is a vertical expansion by 3. The B value is 2. This is going to help us find the new period, the new length of our wave. So originally we know that our wave is 2 pi in length. To find the new period, we need to take 2 pi and divide it by the B value that we are given. In this case, we are dividing by 2. So this tells us pi is the new period. So this represents a horizontal compression because we were started at 2 pi and we're squeezing our graph down to 1 pi. Then looking at our H value, it's pi by 6, but there's a positive sign there. So this is telling us that we are going pi by 6 to the left. And our K value is negative 6. And because it's negative, that means we're going down. Okay, so these are all the pieces of information we need in order to graph our sine function. The next thing I need to notice is the graph and the scale of the graph. So notice that this is our y-axis and this is -1. That means all of our squares are worth 1. This is -2, -3, -4. I'm going to go all the way down. -5, -6, -7, -8, -9. Okay. And our x value, or x-axis, I should say, is up here. You'll notice that this is not the center of the graph, right? And that is because we know that we are going to be moving down 6 spots. So we need to move our axis in a way that we'll be able to see the entire graph once we've moved it. You'll also notice that they say the label, the scale here is pi by 6. It's important to choose a scale that makes sense for our graph. So 2 squares are worth pi by 6. So 2 squares makes 2 pi by 6. 2 more squares is 3 pi by 6, or pi by 2 is another way to write that, right? 3 pi by 6 is the same as pi by 2. Then I have 4 pi by 6, 5 pi by 6, 6 pi by 6, or just pi, right? I want to know where my key points are. And then I'm just going to keep going right to the end here. This is 7 pi by 6, 8 pi by 6, 9 pi by 6. And 9 pi by 6 is the same as 3 pi by 2. Okay, so where you see my green note, this is 90 degrees, 180 degrees, 270 degrees. You'll notice we've run out of space, so we don't actually have enough space for 2 pi, which is okay because we know we're compressing it down to half its length, right? So we have a scale, we have the directions and compressions that we need. So let's go on to graph this transformation. This is a sine graph. So first I'm going to just sketch in my original. It starts at 0, 0. At pi by 2, it's 1. At pi, it's 0. At 3 pi by 2, it's -1. So I don't have enough room for the whole thing, but that's okay. I just need to know where my base of the sketch is. When we learn transformations in Unit 1, we remember that we do them in order of ERT. We do expansions, we do reflections, and then we do translations. So stretch it, reflect it, and then move left, right, up, or down. So let's start with our A. Our A is a vertical expansion by 3. So the zeros don't change, but our highs and lows change. So rather than being at a high of 1, I'm going to be now at a high of 3. So this is 1, 2, and 3. Slightly off the grid, but that's okay. 1, 2, 3, slightly off. So we're slightly taller. I should be doing this dotted because I don't need the whole thing there. So A stretch done. The next thing I do is my B stretch. And the way that I do that is by marking out where is the beginning and end of my graph. My beginning is 0, 0. The end is pi rather than 2 pi, right? Because I'm squishing it down. Now, where is the middle of my graph? What's between 0 and pi? Pi by 2. That's the middle of my graph. Okay, looking at our original sine wave on the board, the top of the graph is between the beginning and the middle. So between 0 and pi by 2. The way I'm going to do this is I'm going to count how many squares are between 0 and pi by 2. 1, 2, 3, 4, 5, 6 squares. So 3 squares is the halfway point. 1, 2, 3. So the top of my wave is right there. 1, 2, 3. Bottom of my wave is right here. Okay. So now this blue line is a vertical stretch and a horizontal compression. So A value and B value done. The last thing I need to do is translate it, right? Because there's no reflections. I don't have any extra negative signs here. So I'm going to do the translations kind of all together. Remember that 2 squares is equivalent to pi by 6. So when I'm moving to the left pi by 6, I'm moving 2 squares to the left. And 1 square is 1. I need to go down 6, so I'm going to go down 6 squares, left 2 squares for all of my key points. So let's highlight my key point, 5 key points. And I'm going to use pink as my final color. I'm going to go down 6 squares over 2 squares. Down 6 squares over 2 squares. Down 6 squares, left 2. Down 6, left 2. Down 6, left 2. So here is my final transformation. One sine graph or one sine rotation with the transformations listed in the equation. Now, the question does ask for 2 cycles. Once you have your first cycle graphed, just follow the pattern. Let's take a look. What pattern can we see? 1, 2, 3. 1, 2, 3. So each rotation is 3 up, 3 over. So I can just keep going. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Kind of ran out of room there. It's a little bit ugly. That's okay. I can go backwards too. 1, 2, 3. 1, 2, 3. So there's 2 waves. Questions, comments, concerns? Are we pretty comfortable with that? Could we replicate it again? Okay. On Delta Math, let me just go back to my screen here. Oh, I closed it. Okay, on Delta Math, there is an assignment called graphing trig equations. We'll come back to it in a moment. I just want to do some word problems because we're slightly running out of time today, okay? But essentially, these are the methods that you're going to use to graph them on Delta Math as well. Let's take a look at a word problem. Notice this. Hint, hint, nudge, nudge. We are going to graph a real-world situation, and then using our picture, we're going to work backwards to write an equation for it. Okay? So let's read some important pieces of information. A Ferris wheel has a radius of 22 meters, and it rotates once every 30 seconds. You get on it at the lowest point, which is 1 meter above the ground. Part A, graph the height as a function of time. So graph the rotation. Write an equation describing the situation. And then C and D is we're going to use the equation to solve for pieces of stuff. So let's focus on the drawing part. You guys know what a Ferris wheel is? It's a carnival ride where there's like chairs on here. And you go all the way around, etc. Okay? So it's telling us that the radius of the Ferris wheel is 22 meters and that you get on at the lowest point, which is 1 meter off the ground. And the time it takes to make one rotation, so all the way around, is 30 seconds. We want to graph the rotation as a function, we want to graph the height as a function of time, meaning on the y-axis we want to see the height, and on the x-axis we want to see the time. I want to ask you, in a real-world situation, where should the point 0, 0 be on our graph? Should it be in the center, at the top, on the left, on the bottom? Think about it. Should we graph it like this, height versus time, or the way that we did our previous example, height versus time, or some other way? Where should the point 0, 0 be on this graph? Where would it make sense? Okay, talk to your neighbor. Can we have negative height? Can we have negative time? So do we need the negative side of our graph? No. So that means we want to use our whole graph to plot positive coordinates. So I'm going to put 0, 0 in the bottom corner here. Now, I have to be able to fit the entire Ferris wheel on the height. What is the lowest height that I can get to on the Ferris wheel? 1 meter. What is the highest point on the Ferris wheel? Close. No. No. What'd you say? How'd you get 45? The diameter is 22 plus 22. That makes 44. How'd you get 45? You have to be off the ground 1 meter. Okay, so we need to be able to fit 45 meters on this scale for height. So to do that, we have to choose how much is each square going to be worth. So let's count it and see how many squares we got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 13 squares. So what I'm going to do is I'm going to take 45 meters and divide it by 13 squares. That gives me 3.46 something, something, something. So a little bit over 3. So I am going to choose my scale, each square to be worth 4. So I have a little bit extra room, okay? So this is 4, 8, 12, 16, 20, 24, 28. Also, if I'm doing math wrong, please let me know. What's 32 plus 4 is 36, 40, 44, 48. Okay, so now I have enough space for my entire Ferris wheel to be on here without running out of room. Let's talk about the horizontal. Horizontal represents time. What is the minimum amount of time I need? 30 seconds. That is one rotation is 30 seconds. So let's count how many squares I got here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So again, I'm going to take 30 seconds, divide by 24. I get something a little bit more than 1. So I'm going to go up by 2s to make sure I have enough room. So 2, 4, 6, 8, 10, 2, 4, 6, 8, 20, 2, 4, 6, 8, 30, 2, 4, 6, 8, 40. Oops, missed a 6 there. There we go. So I'm just going to put some in between numbers. You'll notice that none of these numbers really fit our graph perfectly, but it does make sure that we are able to see the full picture. 26, 28, 32. Okay, that's enough. Once you get to 32, you're good. Okay, now let's graph a real scenario. At the time 0, when you get onto the Ferris wheel, how high are you off the ground? 1 meter. So my first dot is going to be at 0 and 1 meter. Now remember, one box is 4 meters, so I have to kind of approximate where 1 meter is. It's not going to be exact, but good enough. Okay, and the way that I'm going to make sure that my equation is accurate is I'm going to label this point 0, 1. Okay, what other point do I know? X first, right? Time is 0, height is 1. What other point can I plot without having to do math? 30 seconds. I'm also at 1 meter, right? After 30 seconds, I have completed 1 rotation. So this is 30, 1. So 30 and 0 represent the bottom of my graph, right? Where am I at the top of the Ferris wheel? Where is the top? Or when is the top? At 15 seconds, right? Halfway between the bottom and the bottom is the top. So at 15 seconds, how high off the ground am I? Somebody said it earlier. 45, right? 1 meter plus 2 radiuses, the top of the circle, 15 and 45. So I'm going to be somewhere here. And again, I'm going to label that spot, 15, 45. Okay, so that's 3 dots. In order to complete a rotation or to graph something accurately, we need 5. So we want to know, when am I halfway? So I know the bottom and I know the top. When am I at the halfway point on the Ferris wheel? How would I find that out? half of 15, right? So 15 divided by 2 gives me 7.5 seconds. At 7.5 seconds, how high am I off the ground? Remember, radius is 22. So I'm at 23, right? 1 meter to the bottom of the ring plus 22, the halfway up the circle. So 7.5, I'm going to be at 23 somewhere here. I'm going to label that 7.5, 23. That's my halfway point. And now you can kind of see the wave taking shape, right? And then I go, okay, 15 plus 7.5, that's 22.5 seconds. That's going to be the other time that I am halfway on the Ferris wheel. So 22, oh, did I write that? Yes, correctly. 22.5, I'm halfway on the Ferris wheel. Yes. Oh, yeah, 7.5 is half of 15. So I just added to 15, right? So each piece here is 7.5 seconds long. This is 7.5 seconds. That's for each quarter. Essentially, you can take also 30 divided by 4, and that will give you the length of each piece. So this is one rotation of the Ferris wheel in using real numbers, real world. Okay, now the Ferris wheel is going to continue going on and on and on and on and on. So at 37, this is 34, 36, at 37.5 seconds, I'm going to be back at 23. Right? And at 45 seconds, this is 42, 44, 46. At 45 seconds, I'm going to be back at the top of the Ferris wheel. Right? This wheel is going to keep on turning. There's even a famous song about it. Right? So now we have an equation that is a wave function. We want to match it to either a cosine or a sine wave. I'm going to let you choose. Which one should we do? Should we graph this as a cosine or graph this as a sine? You want to do a sine wave? Okay, so a sine wave starts in the center, goes up and then down and then back to the center. So looking at my picture, this makes the most sense. Let us write an equation for that blue piece because it matches the shape of the sine wave that we recognize. Okay. So we are looking for amplitude. We are looking for the B value, which is 2 pi divided by the new period. The A value is the maximum number minus the minimum number divided by 2. H is just where is the starting point of the blue wave. And K is the center. Or we can write it as max plus min divided by 2. I'm going to give you like a 2-minute head start. Can you try to find some of those numbers and start putting them into the equations to solve? Amplitude, the height of this wave is going to be represented, if you can kind of visualize it here, the height of the wave or the height of my circle is going to be the same thing as the radius. So 22 meters. If you did not recognize that from the picture or from the sentence, you could have taken the points 45 and 1, right? The height difference between the top and the bottom of the wave to determine that value. So this is A is 22. For the B value, we know that one rotation takes 30 seconds. So my new period is 30. So 2 pi over 30, I'm going to reduce that fraction. This is going to be pi over 15. That's going to be our compression. The H value is the starting point of our sine wave. Where does it start? It starts 7.5 seconds into the rotation. And because the graph is shifted to the right, then my H value is going to be, what is it? Positive 7.5. But when I put it into the equation, it's minus H, right? So it's going to be minus 7.5. And the center of the graph, again, the center of the graph is right here. How high is it off the ground? Which we've talked about already, and you can see here the center point. This is going to be 23 meters. And again, if you did not know that, you can always take 45 plus 1 and divide that by 2. Okay, so the middle of my graph is at 23, the height of 23. So my final equation, y equals 22 sine I by 15 x minus 7.5, or even, actually here, let me just finish writing, plus 23. If I wanted to be even more specific, what I could do is erase y and call it h as a function of t rather than f of x. And instead of x, I could write t, because this represents time and height. Okay, so we have done A, we have done B, and now it's asking in C, what is your height after 38 seconds? Well, I can just take my function here. I could put 38 right in this spot, throw it in my calculator, and it would tell me the answer, which I'm not going to do right now because I want to focus on the graphing part.